Hello everyone, I'm Jose Miranda, and I'm excited to show you some details about the paper Image Super Resolution Using Very Deep Residual Channel Attention Network, (RCAN), by Zhang and collaborators. Here's an outline of everything we'll cover. We'll start with an introduction on image super resolution, a brief overview of CNNs for SR techniques. We'll introduce RCAN, a state-of-the-art method for SR. We'll break down the model into its components, the residual and channel attention. And finally, we'll see some experiments and results demonstrating the effectiveness of this method. Super resolution, or SR, is a process with the goal to reconstruct a high-resolution image from its low-resolution counterpart. It's a complex task due to the need to infer missing details that are not captured in the low-resolution image. This is complex because SR is an inverse and ill-posed problem, where many potential high-resolution images could correspond to one low-resolution image. However, with the development of deep convolutional neural networks, CNNs, we've seen a paradigm shift in this field. CNNs are well suited for data with a grid-like topology, such as images. Their usual structure can be roughly broken down into its components. The convolutional layers, where these layers perform convolution operations using learnable filters, also known as kernels, which perform feature extraction from the input image. Upscaling increases the dimensions of the data and help with the learning of high-frequency features by the following convolutional layers. It's also responsible for the upscaling of the image to the proper size of the HR image. Inversely, downscaling can be used for dimensionality reduction. This helps with the extraction of low-frequency features in the following convolutional layers. We can also have skip connections that help propagate the low-frequency information from the LR image throughout the network. Now, let me introduce the RCAN, or Very Deep Residual Channel Attention Network. It introduces a new approach to super resolution. The figure 2 represents the network structure with the flow of information through the residual groups, RGs, that compose the residual and residual structure and the residual channel attention blocks, RCAB. It shows their low-resolution input passing through the network to yield a high-resolution output, with each block designed to refine the feature maps progressively. The residual and residual design allows the network to be very deep without running into the vanishing gradient problem, by incorporating both long and short skip connections. The short connections help in learning fine details by skipping over a few layers, while the long skip connections bypass entire blocks of layers, preventing the dilution of low-frequency information. The channel attention mechanism is also introduced in this work. Unlike traditional methods that treat all features equally, CA allows the network to focus on more informative features. It adaptively rescales channel-wise features by considering the interdependencies among channels. This mechanism is crucial for improving the representational ability of the network. In the left, we have the RCAN architecture with pseudocode that we will use to explain some of the technical details further on. Now let's detail the model's processes mathematically by dividing it into steps. First, we have shallow feature extraction. Here, H sub SF represents the shallow feature extraction operation, applied by a convolution layer to the low-resolution input I sub LR, resulting in an initial feature map F sub 0. These initial features are then processed through the residual and residual group, shown both in the diagram and the pseudocode in red, to produce the deep features F sub df that equals to H sub RIR of I sub F0. Finally, we have the upscaling of the features. The deep features F sub df are then upscaled by the upscale module, highlighted in purple in the pseudocode and in the network diagram. The super resolved image I sub SR is reconstructed from the upscaled features using a convolution layer by the operation H sub REC, which is highlighted in gray, and corresponds to the last layer in the diagram. The authors use the L1 matrix norm of the residual between the HR image and the SR output as a loss function. This optimizes the network to produce an output that closely matches the high-resolution target image. Now let's focus to the residual and residual structure. The deep features are processed through a G number of residual groups. Each residual group is a function H sub G, which itself contains multiple layers of operations and individually play the role of enhancing the previously learned features. These groups are indicated by the green text in the pseudocode and correspond to the RG1 to G blocks in the diagram. To facilitate the flow of low-frequency information and aid in learning high-frequency details, the model employs long skip connections. This allows the model to add the output of the shallow feature extraction layer, F sub 0, directly to the output of the current residual and residual group. The output, denoted as F sub df, is equal to F sub 0 plus W sub LSC times F sub G, where W sub LSC are the weights for F sub 0 in the long skip connections. In each residual group, there are a B number of residual channel attention blocks, RCAB1 to B, which are designed to recalibrate the feature maps by focusing on more informative channels. Each RCAB block, represented by the pink text in pseudocode, processes the output of the previous block in sequence. In addition to the long skip connections, short skip connections are used within the residual groups. They allow each RCAB block to learn residual information by adding the input of the block directly to its output, enhancing the model's ability to learn fine details. This is highlighted by the teal text in the pseudocode and is represented by the short skip connection arrows in the RCAB blocks. Each residual channel attention block, RCAB in pink, is structured to process the previous input feature maps, F sub G and B minus 1, and output refined feature maps, F sub G and B, which are then used in subsequent layers. X sub G and B are the output of the residual component, which are the two convolutional layers with a ReLU layer in the middle, illustrated in green. Each residual component outputs a feature map by adding the learned residual to the input of the block, mathematically represented as X sub G and B equals to W2 sub G and B times theta of W1 sub G and B times F sub G and B minus 1. We now focus on the channel attention mechanism within the RCAB. The CA block begins with a global pooling layer, which aggregates the spatial information of feature maps to a single scalar per channel. This is represented as the average of all the values of the feature map. H sub GP is the global pooling operation applied to the feature map, X sub C. The gray text in the pseudocode and the gray layer illustrate the global pooling process. This is followed by the gating mechanism, which uses a two-layer fully connected neural network to learn a channel-wise set of gating weights. This process is represented as S equals calligraphic F of W sub U times theta of W sub D times Z. Here, calligraphical F is the sigmoid function activation function, and theta is the ReLU. The learned channel statistics S are then used to rescale the input features X sub C by an element-wise multiplication with the feature map, X sub C. This is highlighted in orange in the pseudocode and by the element-wise product in the diagram. Channel attention was introduced in this paper and helps the neural network to focus on the most relevant features for reconstructing high-resolution images. In practice, the CA allows the network to adaptively rescale the feature maps, improving the results. The authors experimented the Arcan architecture without and with CA, denoted as Arcan Plus in the results. Let's discuss some of their experiments to validate the model. For training, they used the DIV2K dataset, which is augmented to increase the diversity of the training samples. The augmentation includes random rotations and horizontal flips. For testing and validation, they employ 5 benchmark datasets. The model is evaluated using 2 degradation models, bicubic and blur downscale. These are downscaling processes used where high-resolution images are not available, so lower resolution quality images are generated from high-quality images. Performance metrics include peak signal to noise ratio and structural similarity index, which are standard for assessing the high quality of super resolved images against high resolution originals. Higher PSNR and SSIM values indicate better reconstruction quality, accurate pixel intensities, and structural information preservation, respectively. Here we see the Archon model's superior performance for a 4x scaling. Visually, the Archon results are sharper and retain details that most other methods fail to capture, such as the holes, windows, and line patterns. It achieves the highest PSNR and SSIM scores compared to the older models, and it's even better using channel attention. Here are the results for an even higher upscaling factor, 8x. Archon's super resolved images are the closest to the original images in terms of both pixel accuracy and structural fidelity. There's less distortion and more detail in textures and edges. And it also still outperforms the other models in this higher upscaling factor. Here we have a performance comparison of various super resolution methods in terms of peak signal to noise ratio against the number of parameters used in the models, evaluated for 4 and 8 times upscaling. Archon achieves the highest performance in both scenarios, indicating superior image quality, even as the upscaling factor increases, which is challenging achievement by itself. The red dots representing Archon are located further to the right compared to other models, suggesting that it utilizes a higher number of parameters, and this may contribute to its enhanced performance. Note that the network size is agnostic to upscale factor. In closing, we took a deep dive into the Archon model and how its architecture is tailored for super resolution tasks using the residual and residual structure and channel attention blocks. We also saw that it outperformed previous SR CNN models, and it was the state-of-the-art model for SR until recently, when it was dethroned by a transformer architecture that also uses channel attention. Thank you very much for listening. I'll be happy to take any questions that you have now. Thank you.